Hello everyone, I'm Ryohei Banno from Kogakuin University in Japan. Today, I'd like to talk about the way to collect a massive amount of data from IoT devices by using MQTT brokers. Internet of Things has been developing in various application fields. For example, some companies have been developing smart factories where they can monitor industrial robots to realize preventive maintenance and to reduce unexpected downtime. Such system is made possible by collecting various data from sensors of those industrial robots like operation time and inside temperature. For collecting data from IoT devices, MQTT is a suitable choice of communication protocols. It provides loose coupling nature by publish-subscribe messaging model, and the header size is quite small compared to conventional protocols like HTTP. MQTT uses an intermediate server called a broker. A receiver is called a subscriber, and it subscribes to the broker by specifying their interest in topics. Publishers send a message with a topic, and then the broker forwards messages to appropriate subscribers. MQTT is a promising protocol, but there is an issue of performance. Typical architecture of collecting IoT data by using MQTT is like this figure. The problem is that a massive amount of data from publishers concentrates on the broker, so the broker might not be able to receive all of published data. Even though the broker can process all data, the subscriber might not catch up with the amount of data from the broker. To solve this issue, we aim to find a scalable IoT data collection method with MQTT brokers. There are existing studies to extend the performance of MQTT brokers. MuMQ is a proposal of a high-performance MQTT broker. It efficiently exploits multi-core CPUs by an event-driven I/O mechanism and avoids the kernel overhead by using DPDK. It can improve the performance of a single broker, but it does not have the horizontal scalability, as well as it requires DPDK-compatible hardware. MQTT-ST and ILDM are using multiple MQTT brokers. They utilize multiple MQTT brokers by connecting them and forming a delivery tree. They are effective if the placement of publishers and subscribers has a high locality. In other words, if publishers and subscribers of the same topic tend to connect to the same broker, they are effective. On the other hand, considering the case of collecting IoT data from many publishers to a few subscribers, they are hard to obtain load distribution. Also, they cause high latency due to multi-hop forwarding among brokers. Here's an overview of our proposed method. To obtain load distribution, we use multiple brokers. Each publisher connects to one of the brokers. The broker to connect to is decided by DNS round-robin, so a publisher does not need additional functionality except for specifying the broker by a domain name. What's more, each application uses multiple subscribers to receive IoT data in parallel. Each subscriber connects to one of the brokers. Subscribers connecting to the same broker make a shared subscription group. Shared subscription is a new functionality appeared in MQTT version 5. It enables to group subscribers of a topic. Each message of that topic is delivered to one of the subscribers in the group. By using the shared subscription, each application can receive IoT data in parallel. To sum up, we obtain load distribution for massive data from publishers by using multiple brokers and DNS round-robin. Besides, we obtain load distribution for massive data from brokers by using shared subscription. To evaluate the proposed method, we have developed a load testing tool named MQTT Loader. It supports MQTT version 3.1.1 and version 5. When you run it, it generates multiple MQTT clients and applies a load on a broker based on parameter settings. We can run MQTT Loader either on a single host machine or multiple host machines. Running both publishers and subscribers on a single host may cause mutual influence, like receiving load of subscribers lowers the throughput of publishers. By running publishers and subscribers separately on different hosts, we can avoid such mutual influence. I'd like to show you a quick demonstration. MQTT Loader is easy to use. You can run it by specifying various parameters in the configuration file. Let me start the video. You can download MQTT Loader from GitHub. After extracting files, you can find the default configuration file. At least, you need to set the broker address. In this demonstration, I set the public broker of HiveMQ. To run the tool, you just need to execute a script. It generates multiple publishers and subscribers and communicates with the broker. After completing to send and receive messages, it automatically calculates statistic data. To evaluate the proposed method, we conducted experiments. We measured average throughput between publishers and brokers, average throughput between brokers and subscribers, and average latency from publishers to subscribers. We used Mosquito for brokers and MQTT Loader for publishers and subscribers. We set the number of publishers 8. Each publisher sends out messages with no interval, where each message has a 600 bytes payload. Each measurement takes 60 seconds and it is conducted 3 times repeatedly. We used 4 cases for comparison. SGL uses a single broker and a single subscriber. SGL uses a single broker and 2 subscribers with shared subscription. MLT-SGL uses 2 brokers and 2 subscribers without shared subscription. MLT-SHD uses 2 brokers and 4 subscribers with shared subscription. The last one corresponds to the proposed method. The hardware information in the experiments is as like this. To apply sufficient load on brokers, we used a relatively high-performance machine for publishers. Here's the result of throughput. Overall, the publisher's throughput is larger than the subscriber's throughput. This means that the amount of published data exceeds the capability of brokers. When focusing on the throughput of subscribers, MLT-SHD achieved the largest throughput. That is, using multiple brokers and shared subscription is effective for collecting a massive amount of IoT data. Next, I show the results of latency. Regardless of the 4 cases, the traffic of QoS level 0 causes significantly long latency. In the case of QoS 1 and 2, MLT-SHD has the largest latency in return for the high throughput. Now I'd like to conclude my talk. We proposed a scalable IoT data collection method with MQTT. We developed a load testing tool, MQTT Loader, and evaluated the proposed method by using it. In the experiments, the proposed method achieves high throughput. On the other hand, the latency tends to become large. Our future work includes a detailed analysis of experimental results and improvement of the latency. Thank you for your attention.